In this lecture, we will continue the review of important functions to be used throughout the course. This time, we're going to focus on exponential and logarithmic functions. If you require a more in-depth review of these functions, please take a look at the pre-calculus refresher modules posted on the Blackboard page. Let's recall that exponential functions are of the form y equals a to power x, where a is a positive integer. So there's a few different integers that we can consider, and I'm going to make just a couple of really quick sketches of what exponential functions might look like. If you have an exponential function, let's say 2 to power x, that means that we're raising 2 to the various powers, 2 to power 1, 2 to power 2, 2 to power 4, and so on. We will be getting the numbers that increase. However, we can also raise 2 to negative powers, which will in turn produce smaller and smaller fractions. So exponential functions will always have a shape that looks like this when the integer that's plugged in here that serves as a base is greater than 1. If it's less than 1, then the exponential function will actually be of the form of the decay function and will be decreasing. So for example, this is 2 to power x, whereas the shape like this will be 1/2 to power x, or alternatively 2 to power negative x. Again, if you need to review some exponential rules, now would be a good time to do so. One of the functions that we're going to be using throughout is the exponential function with a natural exponent, e. E is just a number, 2.718 and so forth. It doesn't have a pattern, it never ends, it goes on forever in the decimal expansion, but this is a very handy function because of how easy its derivative is and a lot of other very nice properties. In particular, this number is exactly such exponential function at which the tangent line at 0 has a slope of 1. That's in fact the defining property of the number e. Now, on the flip side, the inverses of exponential functions are what we call logarithmic functions. So let's think about that process for just a second. If I have a function y equals 2 to power x, the way to compute it is I simply raise 2 to power x, which means that if I'm interested in its inverse, I don't raise something to the power, I think of the power. So logarithm of base 2 of x is precisely the power to which you have to raise 2 to get x. Logarithms can be difficult to deal with if you haven't had a lot of practice, but they're really easy to practice with, and in particular if you think about the definition of where they come from. So let's do a couple of simple calculations. For example, logarithm base 2 of 8. According to the definition, it's the power to which you have to raise 2 to get 8. Well, we all know that 2 cubed is 8, which means that the power to which you have to raise 2 to get 8 is 3. And that is the actual value of the logarithm. In fact, these are the two equivalent forms of writing two things down. One in the exponential, one in the logarithm. Let's try another one. What if we have, for example, logarithm base 3 of 1? So to which power do we have to raise 3 to get 1? Well, raising anything to power 0 will produce a 1, so 0 would be the value of the logarithm here. Now notice that you can't always compute something, not necessarily, so it's easy to note that logarithm base 3, for example, of 0 is not something that we can compute because there is no power to which I can raise 3 to get 0, which means that this logarithm does not exist. Similarly, if I have anything negative in the logarithm, that's not going to produce any kind of reasonable output for the logarithm. So logarithm is only defined for inputs that are strictly greater than 0. That is one of the restrictions on the domain. X has to be strictly greater than 0 here, whereas there was no restriction on the domain for the exponential functions. Rather, the range of the exponential function, as can be seen here, are all the positive numbers. I'm never entering into the negatives, and that is exactly what becomes the domain of its inverse. However, logarithms can, in fact, be fractional or even negative. For example, let's say if I have logarithm of 1/2 of 2, I have to think of what power do I have to raise 1/2 to get 2. And I can see that in order for me to go from 1/2 to 2, I simply have to flip the fraction. Flipping the fraction corresponds to the negative power, and in this case, to simply minus 1. So the logarithm, while it cannot have negative inputs, can have a negative output. In terms of the graphs, recall that exponential functions, inverse functions have graphs that are a reflection of their original function. So if I start off with a function e to power x, then in order for me to get the natural logarithm, so the inverse of that, all I have to do is take the line y equals x and flip my function in that line. So I can think of that as if I drew this function in wet ink and I folded the paper along the diagonal here, where I would see the trace of my function is what the inverse would be. So all the points will be exactly those flipped in my blue, in this case, line y equals x. Now this time I'm going to produce the inverse of the natural exponential function, and that is something that we call natural logarithm of base e of x. And because it's something we use all the time, we have a bit of a shorthand for it, ln of x, natural logarithm of x. Notice a couple of very important points here. For the exponential function, the y-intercept will always be up at 1 because anything, in fact, raised to power 0 will produce a 1. That means that this point will get transferred to the logarithmic one that corresponds to the x-intercept of 1. And that is because, as we've seen here, raising anything to power 0 will always produce a 1. Now, logarithmic and exponential functions do have quite a few properties that are very useful when it comes to solving equations that involve these functions and also just performing various simplifications. So these are just a list of properties of these functions that I encourage you to go through. These are very familiar exponential properties, these are very familiar logarithmic properties, and they include so-called cancellation properties, which really are just the properties of inverse functions. If two functions that are inverses of each other are applied one after the other, then the outcome will just be their original value. So if logarithm and exponential function are applied immediately one following the other, the outcome will just be their original input. Here we can also recall that the derivative of the exponential function e to the x is just itself. You can think of the e to the x as being a very egoistic function. Its derivative is simply itself. And the derivative of the logarithm is 1 over the inside. Now, of course, when we deal with derivatives, we're going to have to recall things like chain rule, and we will see a few applications in a minute. There is a worksheet that's attached to the print version of the slides that I encourage you to go through for more practice of going in between the exponential and logarithmic form, of thinking about how logarithms and exponentials compare, and of various ways to simplify as well as solve equations and find derivatives of these functions. All of these skills are going to be essential for us to practice more complex skills with these functions. Now, I'm going to do just a few examples to get us on track with recalling how these functions work, but please do practice more with them. So in the first two examples here, I have equations that I would like to solve for x. The first one, I have e to power 5x is equal to 7. Now, while there's a few ways of actually solving it, one way is to apply logarithmic function to both sides of the equation. So I'm going to take it step by step and write everything down. So I'm going to apply logarithm to the left-hand side, and I'm going to apply logarithm to the right-hand side. Now, on the left-hand side, what I have now is that the logarithmic and exponential functions are applied back-to-back to 5x. So you can either apply the cancellation rule, or you can also apply the rule that says that I can take the power inside the logarithm and move it all the way to the front. Either way, what we get on the left is 5x, because even if I move the power down, what I have left is logarithm ln of e, which is just 1. And on the right-hand side, I'm going to have ln of 7 remaining. Now, ln of 7, as your calculator will readily tell you, is just some sort of a number, so I'm going to leave it like that. I'm not interested in the decimal solution of it. I'm simply interested in the solution. So all I have left to do is divide both sides by 5, and this is now my final solution to my original equation. If I have a solution in terms of a logarithm, I will do basically the exact same thing, but with the exponentials. If I start with a logarithm and I'm interested in solving for what's inside of it, I have to take e to the power of both sides of the equation. And then again, on the left here, what I have is that the exponential and the logarithmic functions were applied back to 5x. So I get simply 5x on the left. And on the right-hand side, I have e to power 7. Again, e to power 7 is just some kind of a number, as your calculator can tell you. I'm going to leave it in this calculator-ready form, and then I can divide both sides by 5 to obtain my equation here. It is good practice, particularly with functions whose domain is restricted. For example, as mentioned on the previous slide, logarithms cannot take in negative inputs, which means that it's good practice to check your final solution to make sure that it's not an extraneous root. So plug that in and make sure the equation actually works. When it comes to taking the derivatives, this is what all of these equations, or this is what all of these exercises are about. You have to be careful about remembering to carry through with the chain rule or any other differentiation rules that have to come up in the process. So what I have here is e to power 5x. Recall that the derivative of e to power x is simply itself. So here, what I can see is that my inside function is 5x, and my outside function is just the exponential function. So the very first thing I can do when taking the derivative is take the derivative of the outside followed by the derivative of the inside. The derivative of the outside, being the exponential function, is simply itself. And recall that just like in peeling an onion, if you take the derivative of the outside function, you have to keep the inside still intact. All the layers get peeled one at a time without first changing the actual inside. And then I have to follow up with the derivative of the inside. The derivative of 5x in this case is simply 5. And so this is my derivative of this function. Let's take a look at this next example here. So I have x times ln x. So the first thing I notice is that there is a multiplication involved here, which means that this will require the product rule to be applied to differentiate this function. The product rule tells us that I first take a derivative of the first function multiplied by the second plus the first function times the derivative of the second. The derivative of the first function, which is x, is simply 1. So I take a derivative and I keep the second function, plus I leave the first function and multiply by the derivative of the second. Recall that the derivative of ln x is simply 1 over x, so that's what I get. I can see, of course, that I can simplify this because, for example, in the second portion, the two x's will cancel and I'll simply get a 1. So my most simplified solution will be ln of x plus 1. Let's take a look at this guy right here. So I can see that there is a ratio involved, which means that I will likely have to apply the quotient rule, or if I so choose, I can rewrite this as x times e to power negative x, therefore turning my quotient into a product, and then I can apply the product rule. I'm going to leave this one to you to finish. So if you choose to take the derivative as is, you'll have to apply the quotient rule. And if you choose to simplify in this way, then you can apply the product rule. Either of these rules will work in this case. But what I strongly recommend is before you jump in to take a derivative, to think about whether it's worth simplifying. For example, in this case, I can of course take the derivative as is. It will involve me taking the derivative of ln as the outside function. So I will get 1 over the inside. And then I will have to follow up, as per chain rule, with the derivative of the inside. Or, alternatively, what I can do is first of all simplify this function and then take a derivative. Now, what I notice here is that the inside is cube root of x, which is x to power 1/3. And then as per logarithmic rules, the power of the inside can come down to the front. So this expression is actually the same as 1/3 times ln of x. Now taking the derivative of this is really much more straightforward, because what I have now is I have the constant, so I can simply rewrite that in taking the derivative as per constant rule, times the derivative of the function itself. And the function itself here is ln x, the derivative of which is 1/x. And I'm done with the derivatives. No need for chain rule or anything like that. So if you can simplify first, do. Particularly with things like logarithms that have a lot of various simplifications rule that go hand in hand with them. Again, for more practice on solving equations and finding derivatives, do take a look at the worksheet attached and at any other pre-calculus review materials you choose to go through. Let's take a look at a couple of applications of logarithmic and exponential functions. One of the biggest applications of particularly logarithmic functions are things that involve logarithmic scaling. These are things that are measured either on a very large scale, for example, Richter scale of earthquake intensity, or on a very small scale, for example, pH balance of chemical solutions. So here we're going to take a look at the Richter scale. Richter scale is calculated as logarithm base 10 of the following ratio. I is the intensity of the earthquake you're trying to measure, and I naught is the intensity of a barely felt earthquake, the so-called threshold. So let's go through a couple of questions just to see how the logarithmic scale works. If an earthquake is 10,000 times as intense as the threshold, what is its magnitude on Richter scale? So what I have, I'm trying to calculate the magnitude on Richter scale, so I can simply, first of all, try to rewrite my formula. Now, I know something about this I in this case. It's the earthquake that's 10,000 times as intense as the threshold. So if my threshold is I naught, then 10,000 times I naught is simply 10,000 times I naught. That is what I put into my logarithm. Now, of course, I can notice here that I can cancel I naughts, and what I have is logarithm base 10 of 10,000. Recall the definition of logarithms is this is the power to which I have to raise 10 to get 10,000. Now this is not too hard to calculate, and you can readily see that this is going to be 4. So that means that the Richter scale of 4 corresponds to an earthquake 10,000 times as intense as the threshold. We're taking numbers that are very, very big and putting them on a scale that is much more manageable. Now, how about if we know the magnitude and we would like to know the actual intensity? The strongest earthquake ever recorded happened in Chile on May 22nd, 1960, with a recorded magnitude of 9.5. How much stronger than the threshold is that? So what I have here is I know that the Richter scale reading, this R, was 9.5. And what I would like to know is how does this I compare to this I naught? So what I have is 9.5 is logarithm base 10 of I divided by I naught. Because I'm trying to get to the inside of the logarithm, I'm trying to get rid of this logarithm in front, I'm going to apply the inverse function to it, which is the exponential function. Now I can raise both sides to power e, but that's not the base here. What will be faster is raising both sides to the corresponding base. So 10 to power 9.5 is equal to 10 to power log 10 I over I naught. So if I haven't done much, I've simply raised 10 to the power of both sides of this equation. So I can still see my equation in the powers here. But next comes the simplification that the exponential and the logarithmic functions are inverses of each other, so they cancel each other's actions, and I simply get what was on the inside. So this equation can be simplified to, on the left-hand side, I'm going to leave 10 to power 9.5, but on the right-hand side, I'm simply going to get I divided by I naught. That means that the earthquake that was measured as compared to the barely felt earthquake was 10 to the power 9.5 stronger than the threshold. The logarithmic scale on the flip side is 10 raised to that power. So this earthquake was 10 to power 9.5 stronger than the threshold. Try putting this into your calculator just to see how big of a number it is. And most likely, if you have a regular graphing calculator, it won't even be able to compute this. Their screen will not be enough to contain all the digits of this. How about comparing two values? So I have how much stronger is the 4.8 earthquake than 4.3 earthquake. So let's go back through the Richter scale and actually compute the corresponding intensities. 4.8, as per my Chile example here, if I start off with the Richter scale, what I have to do to get to the intensity is raise both sides to power 10. So that means that 4.8 earthquake is actually 10 to power 4.8 times the threshold, and 4.3 earthquake then respectively is 10 to power 4.3 stronger than the threshold. So if I'm interested in respective intensities, I can simply divide the two by each other. So I have that 10 to power 4.8 divided by 10 to power 4.3, which, according to the exponentiation rules, I simply subtract the powers. So I'm going to get 10 to power 0.5, which is approximately 3.16. So that means that a 4.8 earthquake is 3.16 times stronger than the 4.3 earthquake. Let's record that. So notice the difference here between 4.8 and 4.3 on a logarithmic scale. It seems not very big, only 0.5%, 0.5 point difference. But that actually corresponds to 10 to 0.5, which means that the difference between these two earthquakes isn't 0.5 times stronger, it's 3 times stronger. And this is the essence of logarithmic scales. Whatever you have in a logarithmic scale corresponds to 10 to that power in the actual absolute numbers. Now, we see a lot of logarithmic scale graphs on news right now with COVID and measuring of the infectious rate as a logarithmic scale, so you got to be a little bit careful about those. This scale here is still the Richter scale, so you notice that 0 corresponds to the earthquake that was not felt, and then anywhere between 2 and 4 is minor, then small, then moderate, strong, and so on. But you notice that the scale isn't what we call linear, so the distances between 1 and 2 are not the same as the distances between 6 and 7, as we would expect on a linear scale. In fact, these distances keep growing and get bigger and bigger and bigger, because what they actually correspond to are powers of 10, not just themselves as numbers. So the difference, for example, between the earthquake of Richter scale 3 and an earthquake of a Richter scale 7 isn't 4 points. It's not 4 times stronger. It's 10 to power 4 times stronger. The exponential or logarithmic scales grow differently, so you got to pay a little bit more attention to what the actual numbers mean. Next, we're going to take a look at a couple of really cool applications that involve exponential and logarithmic functions. The first one is firing range of a neuron. Neurons communicate with one another at junctions that are called synapses. So here I have one neuron, the one that wants to send the message, and the other neuron, the one that wants to receive it. The junction, the synapses, happens right here. So this is the zoomed in version or picture of that. Now, most synapses are chemical, some of them are electrical. This is the setup for the chemical synapses. So what happens is the neuron that wants to send the message actually does so through the neurotransmitters. And the more neurotransmitters there are, the more likely the actual messaging is going to occur. What is really neat is that we actually have mathematical functions that describe the average firing rate of a neuron in spikes per second as a function of concentration of these neurotransmitters that perfuse the synapses. Okay, so this is the function, and of course, as you can see, it involves exponential functions here. Remember that x is the concentration, so it's got to be positive, and the overall outcome is going to be the spikes per second firing rate of a neuron. Let's take a look at the questions that are associated with it. Find the horizontal asymptote of this function and discuss its biological meaning. So recall that for horizontal asymptotes, much like with rational functions that we talked about last time, there's only one method of finding them, and that is to take the limit as our variable goes to infinity or negative infinity, but in this case, negative infinity doesn't make sense as x is the concentration of our function. So what I have here is I'm just going to rewrite my function here and then analyze what happens there. I can now perform the same type of power analysis as we did last time. For those of you who remember L'Hopital's rule from Calculus 1, you can also apply it here, but the power analysis actually gives a much cleaner way of computing this limit. So what happens is, let's take a look. As x goes to infinity, the top, there's nothing I can choose from, much like in Hill functions analysis of power domination, but on the bottom I have two terms. Now, e to some power grows obviously a lot faster than 2 will. Try plugging in any large number like x equals 100, and you will see that this number will clearly dominate a constant, any constant, but in particular 2. So at infinity, the one term that's going to dominate on the bottom is going to be e to power 3x. And now once I'm down to here, I can see that I can simply cancel 3e to the 3x on top and bottom, and overall I get limit as x goes to infinity of 20 or just 20. So my horizontal asymptote is 20, which means, as it's asking for the biological meaning, that the average firing rate of the neuron as the concentration of neurotransmitters becomes very fast approaches 20 spikes per second. Now let's take a look at the second part of this question that's asking to sketch a rough graph for this function and then discuss the derivative. Now, of course, we can throw all kinds of Calculus 1 tools at this function to produce a reasonable sketch of it, but we can also ask Desmos to simply sketch it for us. Here's the sketch of this function. I have adjusted the scale to see a meaningful picture here, and this visually confirms the fact that our computed horizontal asymptote was at 20. So let me take the portion of this graph and paste it onto our slides here. There we go. So obviously, I am not interested in the negative values for x because x stands for concentration, and I'm really only interested in the graph until the horizontal asymptote behavior becomes very obvious. So what can you say about the derivative as x increases? The derivative of the function, first of all, represents how fast the firing rate increases or decreases, the rate of change. On the graph, the derivative represents the slope of the tangent line. So let's think about tangent lines here. If I draw one at the beginning, it's fairly steep. I can see that it's probably the steepest somewhere around here, and then the tangent lines become flatter and flatter and flatter as the function approaches its horizontal asymptote. This behavior is reminiscent of the Michaelis-Menten kinetics, or any kind of Hill function really, and recall how we discussed the Michaelis-Menten kinetics in that at certain concentration, the gain in velocity at which the chemical reaction takes place, or the firing rate of a neuron that can take place, is basically limited. So in terms of the derivative, it first increases as the tangent lines get steeper, and then as x goes on and the concentration gets higher and higher and higher, the derivative remains positive, but is now getting less and less steep. This is for the firing range of a neuron. Let's take a look at another application of cardiac output. Cardiac output is the volume of blood pumped by the heart per unit of time. And one of the methods to, in fact, measure it is so-called thermodilution. The doctors will insert an actual tube into the heart, which sounds like a very invasive procedure, but apparently is quite standard. And then they will, in fact, simply add just a little bit of cold dextrose solution directly into the heart and then measure the temperature on the exit. What they're actually measuring is how fast the heart is able to warm up the cold dextrose solution, and that, in fact, then of course measures how fast or how efficiently the heart is pumping the blood out. Again, because it's one of the standard procedures, it is well known to be modeled by specific mathematical functions. So a typical temperature variation curve during thermodilution is given by this function, 0.02 t squared e to power t degrees in Celsius, where t is measured in seconds. Okay, so what's important here to realize is that this is measuring the below normal temperature. So we're interested in when this is going to get back to zero, which basically means normal temperature. The faster it gets back to zero, the more effectively and efficiently the heart is pumping up blood. We are asked to compute and interpret the derivative at 0 and the derivative at 3. So let's take a look at what we can do. Let me rewrite my function so I can annotate along with it. So I would like to take a derivative of this, and recalling our differentiation rules, I can see that this is first of all a product. So I will have to apply some kind of a product rule on it. Now I am going to choose to take the coefficient with the first function here, but it really doesn't make any difference. So if I take the derivative of my function in general, what am I going to have? I'm going to have the derivative of the first piece, which is going to be 0.2 times 2t, and then I'm going to leave the second one alone, plus I leave the first portion alone, times I take the derivative of the second function in the product. Now here, the derivative of the exponential is itself, but then I have to keep in mind that I have to apply the chain rule to the inside. So it's going to be itself times the derivative of the inside, which in this case is just -1. Now I can rewrite this function, and I can of course simplify this a little bit. I can see, and if I was doing the full first semester calculus analysis on it, I can see that I can even take out common terms here, which will make it easier for me to solve for critical points and whatnot. But I'm not asked to do this here. I'm simply asked to find it and interpret it at 2 different points. So first of all, before I even start plugging in numbers, I can start thinking about what are the units of this function's derivative now. The units of the original function were the degree Celsius. So this is degree Celsius. The derivative now is taken with respect to t, which is measured in seconds. So again, sometimes the other notation is probably easier to think about when you want to think about units. D capital T by D little t. The units of the capital T were degrees Celsius. The units of the little t were seconds. So what the derivative, of course, is measuring is degrees Celsius per second, the rate at which the temperature is coming back to normal in degrees Celsius per second. If I calculate this now at 0 and at 3, what are going to be the numbers? At 0, I don't even have to pull out my calculator. I can actually do these calculations from here. This is 2 pieces. This first piece has t in it, so t being 0 will make the whole piece 0, and there's a t in here as well. So t being 0 will make this whole piece 0 as well. So at 0, I have 0 degrees Celsius per second. Okay, it makes sense. Before the process begins, or at the very beginning of the process, the temperature is not actually changing. If I compute this at 3 now I'm going to have to plot a calculator or ask Wolfram Alpha for help. If I plug in 3 into here and get the actual number, I'm going to round it up to 2 decimal places, and what I have is negative 0.03. And again, my units are degrees Celsius per second. So the derivative at 3 seconds is negative. Let's unpack a little bit what that means. If I plug 3 into my original function, I notice that this number being produced is going to be positive still, which means that at 3 seconds, the degrees below normal temperature are still positive, so the heart is still working on returning back to the normal temperature. However, the rate at which it's doing so is negative, which means it's decreasing. So we are now on the actual curve where the temperature is coming back to normal. The abnormality is decreasing. In order for us to better understand functions like these, it really helps to graph it. Of course, we can graph this using all kinds of first semester calculus tools, and in fact, we graph this function in Math 111 in the Life Sciences version, but in this case, we're just interested to understand this a little bit more. So we can call on Desmos, to graph it for us. Here it is, scaled to some reasonable degree. Notice that when you enter functions into Desmos, you have to use x as the variable. So if it was t in the original, it has to be x here. And let's just take a look at what happens to this function here. The maximum occurs somewhere around 2. So at approximately 2 seconds, at least visually according to the graph, not necessarily exactly 2 seconds, it looks like that's when the temperature of the heart reaches its furthest below normal temperature. Up until then, the temperature is getting lower and lower below normal, and afterwards it's coming back to normality. Let's copy this graph over into our slides to better analyze this for a second here. So what we have at 3 seconds is we are somewhere here on the curve. And then of course here, I can see that the tangent line is in fact going to have a negative slope, which corresponds to my calculations of the derivative here. So along this line, that's when the temperature of the heart was dropping below normal. And then after this point, it is returning to normal until it eventually plateaus at being normal. This is just 2 of the applications. We're going to see more. Once again, let me remind you that we're going to be dealing with exponential and logarithmic functions a lot in this course. So take the time now to really review them and be sure that you're proficient with solving equations, taking derivatives of them, and then sketching them using a variety of technological tools.